let's oh, let's start our fourth day on Fortran, on modern Fortran, talking about distributed parallelism, something that is called MPI. So as I told you during the last 3 days, parallel computing is central for modern scientific computing. Most of the codes that you will see on the cluster that are really, really high performance computing related are MPI codes. So all those codes in physics, for materials, for astronomy, codes in chemistry for molecular dynamics, in engineering, computational fluid dynamics, finite elements. Most of those large codes support MPI. So they work in parallel, and usually the way they support parallelism is through MPI. So MPI is the ultimate way, or distributed parallelism is the ultimate way of getting parallel computing, because you are not constrained to use just the core that you have on a single machine. You can use also other machines, more machines that are connected through a certain network and to perform a single job, to orchestrate a single execution using multiple machines. But in the cluster, using all those different nodes available there. So what we will do today is a relatively classical presentation on MPI from the Fortran perspective for Fortran. So MPI is available for, officially is available for C, C++, and Fortran. There are things like kind of wrappers or something called MPI for Python and things like that. In general, this kind of the programs that actually use MPI are written in hard languages for performance considerations. So we will divide this on this. We will present MPI in general, the kind of elements, the concepts related to this. And in this first hour, we will talk about the basic commands, about the basic functions or routines that are used most of the time in MPI. And for the second hour, we will discuss about some extra collectives and groups and communicators, a little bit more, a couple of examples on that. So MPI has been around for a while. It's been the first standard was around from the 90s. At that time, several competing alternatives were around. PDM was one of them. And there are a few that still are in use today. But MPI is the dominant technology for distributed parallel computing. In particular in scientific environments. So another thing that we will do is that all the codes that we will see, for examples, have been updated for the latest version of, or one recent version of MPI, MPI 3, and they are using the Fortran 2008 standard. So you will see some difference if you search on internet for other examples that use the old Fortran 90 bindings. So MPI is a paradigm for distributed computing. So compared with OpenMP, which is meant for distribute and execute for parallelism inside a single node, or OpenACC that includes parallelism on a single node or using external accelerator that is also attached to that node, like a GPU. MPI is a completely different approach. So now we are creating a code that when it runs, it will run multiple copies or multiple processes, eventually on different machines, and they will communicate to each other via messages. So there is a network in place, and somehow, and that's part of the architecture of this, they will have an infrastructure that allows those processes that belong to different machines to communicate and exchange data between them. And that is one thing. MPI is just a standard for a library. So there are multiple implementation of that standard. OpenMPI is just one of them. There are a few others. Originally there were more, but some of them merged in a single development. Some of those developments come from universities or research labs. So there are not too many actually, but there is not a single one. So that's the point. It's not a single standard, and there are several implementations of that standard, but all of them will have the same API. So they will all respect the names of functions, the names of the subroutines, and variables, and that ensures you that you can program a code with them for MPI, and that code will work no matter which compiler on MPI implementation you use for that. So MPI is not a programming language, and it's not an extension of a programming language. We saw yesterday that there are ways for making parallelism in Fortran, using, for example, core arrays, and there are things that extend the language, like, for example, the Q.Fortran, that you add things, functions, and some special notations that are not part of the language. That's not the case in MPI. It's not a programming language. In fact, that library, the standard, was written in a way that it could be implemented on in different languages, actually. C, C++, they are similar, not exactly equal, but they are very, very similar. And the implementation of Fortran is also similar to them, but with the particularities of how Fortran works. So originally, before to the MPI 3, this is how you use MPI. So you add like a small, let's see if I can make this slide. This is how you insert MPI into your Fortran program. Nowadays, what we use, and probably you will see this on the code, this is slightly different. There is a new module for it for Fortran 2008, and that's what I'm using for all my examples here. And before that, there was like an include, it was like a preprocessor include that you can use for Fortran. That is, let's say, kind of old, so I will not even show that. The idea of communication is in MPI an abstract concept. So when you can run programs with MPI on your own computer, so you don't need multiple nodes, multiple computers. You don't need a cluster for it for running these examples. In fact, if you just install, for example, on your Windows machine, the WSL, the Windows subsystem for Linux, and you install Ubuntu, there you can install, for example, OpenMPI, that is one of the packages in the repositories for Ubuntu, and you can run all these examples there. It's perfectly fine. You don't need a cluster for this. The cluster will just give you a lot of resources for testing, let's say, big calculations. That's the only difference. But not multiple nodes are necessary. In fact, many of the programs that we run today, in chemistry, physics, even engineering, they usually run perfectly fine on one of our compute nodes with 40 cores. And 40 cores will be just what they need. In fact, there is a kind of a small penalty in using more than one node. That's one thing, and that is one of the things that eventually will become clear. And that's even if you don't program, it will. Even if you will not program in MPI, understanding those concepts will help you to better understand why your code, like Fluent or chemistry code, behaves. It behaves when you move into multiple nodes, and which are the decisions that you should be taking before asking for more nodes or more cores or So there are basically three pieces on MPI, so three different things to consider. One is that when you are working with MPI, usually the implementation will create some wrappers. So in the case of GCC, for example, OpenMPI, will create a wrapper called MPI F90. In the case of here, MPI F90. In the case of Intel, if you are using the Intel implementation of MPI and the Intel implementation and the Intel compilers, Intel Fortran, this is the name of the wrapper. So this one or this one. And we will see that when we start executing codes with this. Another thing, now when you compile the code, so you have the binary, and to run that, you usually need runtime MPI execution. That is usually what you do when you execute MPI run or MPI exec. So a lot of things. Oh. Okay, I'll read you. Oh, yes. So here, when I mention here that this is an abstraction of communication, it means that you not necessarily are using a network. Actually, so you are not communicating this machine with this other machine, and it's necessarily you are transferring data between two different machines. The communication could be between one machine and itself with different processes. So let's say that they develop this infrastructure in such a way that process needs to communicate somehow. If they are using let's say shared memory, or they are just communicating through sockets, or they are using an actual network for doing that, and which kind of network they are using, that's another thing. That is not part of the interface, so of MPI. They need to communicate. They need to communicate somehow. So that is what you call an abstraction. You are not going into the details of what exactly you have to use for making this communication to happen. But I hope that this clarifies things. So in this, for example, you can take these codes and execute them on your own machine, and it will run. And in fact, what is happening are all those processes communicating to each other on the same machine, on the same CPU. So their processes communicating all without an actual network. That's the point. But this in general will require some machinery in order to execute a process on a different machine. And for that, you need something like something that makes an SSH connection or something on the remote machine to execute the process and enabling the communication. So MPI implementations will provide all that. Usually you need to facilitate things, you need like a distributed file system. So all the machines will see the same folders, where the process or the package or the binary could be found on every single machine. So that's why that this typically works on clusters like this, or you have a distributed file system, and all the machines are able to see the same files and the same executables easily. So okay. So let's start with an example here. So this one, I think this example 01. Let's start with this. Let's compile it, let's run it, and after we will come back and understand what is happening here. So this one will be example 01. I will go here. Let me see. This one's stuck, right? Okay. So here in files, MPI, let's start with examples. Same code here. So this one. So as I told you, I'm using the new interface, the new module in Fortran. So this is called model Fortran. So I will not use the old module for this. So a few things change, and we'll tell you what kind of things have changed in this. So this is my classical example of a code that is compiling. It's just showing. Let's see what this does. Yeah, it's computing an array, and each rank is basically telling you what is the sum that I got for that array. It's something simple. Let me see. Let's go here. But we will go here and understand this code. So how we run this? How we compile this? So let me see which modules I have here. We have nothing. Well, that one. Module load, and let's see. Let's compile it with. Let's start with Jesus. 11.1, and I need also the MPI implementation. So I open MPI. Let's start with this one. Well, let's start with the most modern one that we have, 4.1. This one. We will see the warning message that will tell you what's going on. So this is what we need. We need a compiler where we can get Fortran, and we will need an MPI implementation. Second thing. Now, compiling this code, MPI F90. This is a wrapper. So this is something that will arrange things for the library, for everything, and will call the actual compiler. So if you execute this, it will tell you, okay, the actual compiler is this Fortran 11. So that's why it's called our wrapper. It's an intermediary, it's a middleman in this process. So we will use it here for compiling this code, example 01. So at the end, if we did this right, we will get this a.out because we never specified any output file. So that is okay. And now we will run this. We will run it. We run like this. MPI run. So we are using this application, this executable. It's actually in a script, but this tool called MPI run, and we declare the number of processes that we need for executing this. We will see a warning there. I will show you what to do about that warning. If you want to get rid of that warning, in the case of OpenMPI, this warning is specific for MPI. We just add some extra lines here that will avoid the message related to a PTL. It's something particular for OpenMPI. Now, what we are doing here, we are getting some messages. You notice that those messages then doesn't appear on any particular order. They are telling you, okay, something called a rank. We will go into detail what is a rank here. And they are having multiple allocations, some, and everything is a little bit without any order. So now let's go and review what this code is doing. So now you know how to run it. Okay, if you wanted to do it another way, it's this compiler, the module loads, compiler latest. If you want to do it with the Intel, is MPI latest. And the wrapper there is MPI i4. Example 01. MPI run. And you get this. Okay. So now let's review this code. Let's start understanding what's in there. So in Fortran, we use something like this, use MPI, that's the old way. In the modern way is using MPI 08. So we will use the bindings that were created supporting Fortran 2008. That's what we will be using in this code. This is normal Fortran, so nothing. You should now know what we are doing here. We are actually using these new kinds here. This is part of Fortran 2008. So that is another thing. So now, this one is something new. This one is the first call that any MPI code should use before any other MPI code. So all the routines in MPI start with this MPI underscore, and this one must be the first MPI call that you do. So it will prepare the environment there. So now, after that, there are two typical lines here in the code. The first one will get the number of processors that were requested when it runs. So notice that when you program in MPI, you don't know in advance how many instances, how many processes will be using for a specific calculation. And the idea is not making the code rely on a specific number for that. You can have a small machine, or the simulation is not big enough, so you can just use 4 cores or 2 cores, and that's okay. But you can also should be able to expand that and ask for 200 cores. And in fact, MPI has been used in simulations that use thousands, tens of thousands of processes. and they divide all that perfectly fine. So you should not force any number here. And this call is basically gathering which was the number that I got when I execute this code, which was the number of processes that were used in this case. Now, this is one. Another line that usually appears in the very first lines of this is, which is the rank. The rank is one number. Notice that when we execute with core arrays, we go the number of the image. When we execute with OpenMP, we can gather a number for the thread that is in execution. Same thing here. Every single process, we have several processes running here. Every single process will receive a different rank, a different number, different integer. And this number, we can use it to differentiate the execution of those codes. So we can use, for example, to take the space. If you are, imagine that you are making a simulation on a structure and you are using finite elements, you can divide the space on different chunks, on different sections, and each of them will receive a rank, and with that rank, we will divide the space. So if you are rank number 1, rank number 0, you will work on the first part of the piece, of the material, of the bridge, or whatever. If you are rank number 1, you will be working on the second section. Number 3 will work on the third section. And the total number of ranks will tell you. So this number will tell you how we will divide, how many ranks we will have there. So for making this division balanced somehow. So this is a unique number. All of them, all the processes will agree on this number. All processes in MPI will disagree on this number. So they will have an individual rank, what they receive. They receive this number. Now, I'm using here is this number here, for example, for printing something that I only want one rank to print. And I decided that that rank will be rank number 0. It doesn't need to be that rank, but I decided that. This is another routine. This is a function, sorry, this is a function that will return a time. So you use this for benchmarking, for timing, for profiling some code. This is something handy. So it's actually gathering a time from the system. Now, so we are printing this. So only rank 0 will print this. Rank 0. Well, this is the master processing and the number of processes around in this world. And this is, by the way, there's the term for this is the word, the communication. By default, is all the ranks belong to the communicator, the word communicator. And I'm printing this. But notice that when we execute this, it's not necessarily printed first. All processes are executing exactly this code. So of course, one process that receives number 1 will skip this part. Will skip because this it is not rank 0, and it will go here and write something else. So it could take a leading position and print first before rank 0 prints here. Enters in this area here to print. So all the processes are running exactly the same code in principle, but they are redirected through conditionals or something. So they will execute something different, but they are basically following the same recipe, the same code. So now other codes here will print this. Which is the rank they are using, and they will allocate a different array here. So notice that I'm doing something here. Each process will allocate a different array. All of them all of them know that they have an array here, so the array is here. But this array is allocable, it has a dimension, but I did it here on purpose. I allocated a different array on each process. So one process will allocate an array, and n is what? It's 1 million. So some of them will allocate 1 million elements on that array. Another will allocate 2 million elements on that array. So they are doing different allocations. That's perfectly fine. And what I'm doing here is I'm initializing the elements of the array with a logarithm, with square root, something that takes some time for allocating. So now at the end, I am asking each rank to make the sum of its own copy of the array. So that's what I do. And at the end, here, when you finish here, when it leaves this conditional here, rank number 0 will print this. Will print that this is the master process, will show the amount of time that it took for making this calculation, and it will finish here. So, and now you will see this call here. This one is the final call of any MPI execution. No more MPI calls should appear after this one, after this MPI finalized. But this one should be the last one. MPI init should be the first one, always. In the case of Fortran, you will see that they have, these are calls, these are subroutines, they don't return anything like functions that do. So they have this integer here, integer I error, that we are not using it, but a more professional code will gather those in case that something bad happens. So to know which was the error condition that was triggered in that case. So usually those things after this will go into a function that will decide if something bad happened. And here, I can still process on print something. Notice that the rank is still something that exists even after MPI finalized. The only thing that you cannot do is execute something like here, like an extra MPI call or something. So this is, let's say, a brief overview of what an MPI code looks like. So now what we will be doing is, so we compile this, and actually here I am showing you examples of how you compile this with different compilers and MPI implementations. So I will not go into this, but yeah, you can use NVIDIA compilers here, or you can use the Intel compiler. So I show you this and the kind of output that you will get. So notice that different ranks are allocating different arrays. So which is a bad idea from the point of view of performance. If you are dividing a domain, let's say the space, if you are computing a bridge or something, and you want this number, the size of the arrays or the size of the points or nodes that you are computing to be more or less balanced. So you want them to keep a balance of that. But I am doing this on purpose to show you that there is nothing that prevents me from making different arrays on different processes. And of course, they will produce a different sum of all those values. And here is finishing. And notice that not in this particular case it was like this, but nothing forced me to having this not being inserted in the middle of this execution. It could happen. So I told you I'm using this MPI F08. Before people use this one, and before this one, they include MPI. This one is now deprecated, and and you should never use this, but you will still will be, you will see this kind of examples around on internet where they use this. So now we talk about this set of functions. So this one is the first one, this one that will gather this number, the total number of processes that are running, and this one is the individual number that the code returns. I'm using this thing for getting a number. So now let's go into something more interesting here. If the machine were just doing something by their own, we cannot go too far. So the good idea here is that we can make these processes to communicate to each other. That's the whole point of a library like MPI. You want, for example, if you are decomposing, you are computing a structure bridge, for example, again, a bridge with finite elements. You will need elements in the middle of one domain to communicate what is happening with the next domain, with the next chunk of the bridge. So some communication needs to happen if you are simulating, for example, some vibration or some dynamics for the structure. So we need communication. There are two kinds of communications. One is what is called point-to-point communication. We will start with that one. So in that case, one process is communicating something to another process. And there are many, but we will show just a couple of routines for that, for sending and receiving data. And there are collective communications. And we will mention a couple in this first hour. We will comment about a couple more on the second hour. So this one is example 02. So this one is, let's say, an academic example. Doesn't do anything. And let's see what is happening here. So MPI 08, normal stuff here. This should be well known now for you. Notice I put an intent in here, a few parameters, and here. I will skip this type. I will describe this in a minute. And this one is particular. This status and data type is something that is required now in the newest standard in Fortran 2008 MPI. This module will require this. Before this, when you were using MPI, if I'm not wrong, this one was an array of integers, and this one was okay. This one was still a MPI data type, but this one changed. So this one is one thing that changed from the old standard to the modern MPI with Fortran. So before was like this. It was an integer MPI status, not MPI status, wrong. Here's a wrong. This one, before it was an integer with multiple values. But I will skip that specific thing at this point. What I'm doing here is that I am communicating one data that is going from one rank to the next one, and that rank will send that data to the next rank, like a ring. So they will go into the next process, communicating a number that will transfer that number to the next element in the process, and the last rank will communicate that number to the rank number 0. So they will close the ring. So number 0 will communicate to number 1, number 1 with number 2, number 2 with number 3, number 3 with number 4. And if number 4 is the last one, that means that we have 5 ranks from 0 to 4. 4 will communicate with number 0. That is what we are doing here. And we are doing this a number of times. And we are keeping track of the amount of time that is spent on this cycling, on this looping. So here you will notice that this one is for rank number 0. Rank number 0 will send the data, this data, and this data is here. It's an array. It's an array. And we decide the number of elements on that array to be this value. So we are changing that value. And here we are probably doing an allocation here of this. So we are allocating here and we are initializing here an array. And rank number 0 will send that array to the next one, destination here. Destination will be rank number 1, right? Everything else, so they are sending this element. This number of elements are in this array, which is the type of the array, something that I skipped for a moment. This one is the destination. So rank number 0, I am in rank number 0. It's sending to rank number 1 this information here. And this one is for the communicator. You always put this, and this is there. So you can forget about this and concentrate on this. And it is basically what to send, where to send it, and eventually a tag or something, a mark that help the system to figure it out if you are receiving multiple things with multiple tags, which one is that particular message. So this is what and where. Now, at some point, when this thing cycles, and rank number 0 will receive something. From where it's receiving it, from the number of processes minus 1. So if we have 5 processes, who is sending that data will be rank number 4. So we are going, this section here is rank number 0 sending data to rank number 1, and at some point is waiting for data being received from rank number 4, but here, and it will cycle again. This is for one of the ranks. Now, what happens with the others? Rank number 1 or rank number 2? Rank number 1 will first start receiving data, will receive data from rank number 0. Source will be rank minus 1. So number 1 will receive from number 0. And it will send data from rank for the next one. It could be rank number 1 or one will send data to rank number 2. In the last case, in the last rank, this will be rank number 4. It will go and return 5, and it was taking the module. So it will go into number 0. So this one is taking care of which rank is receiving data and to which rank is sending data. And here is receiving data from one rank and is sending data for another rank. Notice another thing that it's important here. I will try to put it in the same screen. Perfect. Right. Rank number 0 first send and after receives. Other ranks will first receive and after send. There is a logic for that. There is someone who needs to store the communication ring. It will be rank number 0. Rank number 0 is first sending data. So this one is sending data. And this one will first receive data. And after sending this data. So if you switch orders, let's say, imagine that you put something here like send first, receive first. This one will send data. but it will not having anything here receiving the data, because this one will try to send data to it. All of them will try to send data. Nobody will go into the next step, that is receiving data, and the process will just stuck forever in a dead end. So this is one of those things that you need to be very careful with who sends, who receives, and how. That's why programming in parallel is far more complicated than just simple programming. That's because that's why this is a little bit more advanced. It is how it is. You need to be aware of those things, who send, who receive, and you need to imagine that all of them are doing exactly the same. So or you need to check which one is on which state at some point. And here, at the end of this cycle, I am deallocating X, because the next thing that I will do here is changing the size here. So they are trying different sizes here. So it's basically like this, but I compress it later. So I am sending messages from different sizes. And there is a reason for this. When bigger messages takes longer to send. So there you can see that sending larger and larger amount of numbers will decrease the performance of the whole execution. So this one finished the module. So all this was a module that was doing this. Now, the main program will be simple, will be the classical thing. I'm using ring, so I'm using the module here. I'm using the new module for MPI. The classical 3 lines that we always see on any Fortran, on any MPI code. MPI need, the size, and the rank. We gathered all those elements and store them. Again, all will see the same number here. All processes will get a different number. Rank number 0 will print this initial message. It's prepared for the ring. It will call the ring. This ring will execute several cycles of those for different sizes, and will return all the results. And the last call, it will be this one. And that's it. So basically, I'm moving all the important code out of the main program, and I'm moving into a process, into a separate subroutine. So I declutter what is actually happening. So all the important things are happening inside this code. So let's compile it and run it and get an idea what is happening with this. And after that, we'll actually execute it on multiple machines, so you get an idea of how this works. Hopefully, I will get 3 or 4 machines quickly. So let's see, module purge. Imagine that I would like to do it using the Intel compiler. Module load compiler, latest, and MPI latest. Okay, MPI 4, I will be compiling with the Intel compiler. Example 02. So notice I will have 20 cases here. All the numbers will be this is for it. Yeah, I will make this. Yes, of course. some of those arrays are quite big. So the last one takes a while and was clearly an issue with the stack. So that's it. So you see the amount of time, an average, so it's making 20 runs of each size. And I'm using 4 processes for here. I am running on the same machine. So in a minute, I will try to run it on multiple machines to see how that goes. And those are the timings that I'm getting. So now you can imagine that if your problem is really tiny, some of those are, you are paying a price for communication. That's why if you are making a simulation and classical and molecular dynamics simulation, and you just have a few thousand atoms, it's worthless to try to run this with 40 cores, or even with multiple machines. The communication will kill you because the amount of time spent on every single time step compared with the extra communication for moving data from one node to another will make the code slower than if you run it with less number of nodes or cores. So not always asking for more is better. This is one of the lessons that we learned when we dig in this. Not necessarily more is better. Let me see if I can get it interactively. Let's say 4 nodes. Let me see. Let me see if I can get it this way. Oh, no. Yeah. I will ask for the 4. Let's get it. I will see if I can get quickly 160 cores for running this. If not, we move to something else. So in the meantime, I will discuss something. Okay, so we work around this code. Now remember, rank number 0 first sent and after received. Other ranks will do the opposite. First received and after sent. And that is because in rank number 0, which is starting the ring, so starting the movement of data. And this code is clean, it's not doing anything important here. It was just calling this, and all the internal functionality is now hidden inside this. What else? Okay, so this is how you compile it with GCC 11, an open MPI. This is how you run it. And if you want to avoid those messages, you can use something like this. It's okay. If you are using the NVIDIA compilers, there are some details here, extra things, the way that they compile OpenMPI that you have to do if you want to avoid some messages, some nuisance around. And from the Intel 2021, this is how you compile it. And this one was the thing that I use to prevent arrays to be on stack. Remember that I mentioned that by default, some compilers put arrays on a stack, and that stack is limited to 8 megabytes, so you can go and that will crash the code. So you will see something like that. Either you increase the stack or you compile this way, so all the arrays go into the heap, and you are no longer constrained on the stack for this. And the output is something like this. And I told you that it here is this send receive, and others are doing receive first, send out. So now, in general, the Fortran 2008 interface for MPI is like this. So this is how you see this in documentation, in official documentation, is something like this, is sending something of any dimension. So the dimension is not declared. It's something that you will not change. So this subroutine will not change its buffer. This one is also something that you will never change. The number of elements, the destination, and the tag associated. So this one is the tag. Now the communicator is an object of this type. It's type MPI comp. It's also an intent in. So they are declaring all those things correctly. And this one is purely intent out. So, and it's optional. In 2008, it was not. So when you are using this MPI F08, this one, I error, is not mandatory. So you can put it or not. It will assume that this is optional. Will take this argument option, so will not complain if the value is not there, if it's not present. And very similar structure from the send you will see on receive. The only thing that changes is this MPA status. So, that will contain information about how this is receiving data, or what is the state of the data being received. So it's an array. It's something that you can manage later with some other functions, but we are not paying attention to that this time. So now, I'm mentioning this. Okay. If you want to be better on this, you can use this IError and compare it with MPI success, and everything will be fine. Now, let me see if I got this. Nice. I will give you some time. Otherwise, I will cancel this and run it and move it to something else. So now, there are multiple variations of those send and receive. By default, the send message is not it's not constrained. Let's say when you send the data here, when you send data here, this send is not blocked. But you cannot rely that the data has been sent just because it passes. So it will execute this and will move into this one. If the data has been sent or not is another thing, that this is not making any guarantee. That could not be the case if the send is really, really big, because what it is doing is putting that in a buffer and after sending chunks of this message little by little, so or with certain size, So the data could have changed. So you should not try to change those values here, because it could happen that those values are not actually completely fully sent to the other side, and you could have some corruption of data. So this send has some particular, but there's variations of those send variations of the send that give you more control on if the call should move into the next call or not. So the case that we use here, MPI send, will not block the execution, except if the buffer space is not enough, so it will be stuck there and waiting for the data to move on from the buffer. So it will copy data by chunks. This one it will always skip. We'll try to send the entire data into the buffer. Otherwise, it will fail. It will not be splitting the data, will not chunking the data. It will just fail. And this one will send directly. So it will not make a copy in a buffer. So it will send directly. It's more efficient. You don't need an extra copy for the buffer, but you are stuck. You are for sure it's stuck there until the whole data is moving into its destination. So it's some sort of safe case. It's slower, so it's most constrained. So if something fails, it's something that you can put in place. This double S send and check if what you are facing, for example, is a data erase or something. Something is overriding before the data being actually sent or something. So this is something that you use, and we know what's happening. You probably don't want to use it. You will go into something like this. And this one, it's a different kind of send, where it needs another process being there waiting for the data. Notice that when this sends data, at least in this example, there is no guarantee that the other processes are in this state, that are in this, are right here in this line, waiting for data to be received. And that one, this kind of more restrictive version, requires having some other process being waiting for that data. So now that will complete, let's say, a small example, and this one, a small example of how that works, point-to-point communication. So now let's move into collectives. This is another set of routines that are often used in MPI execution. So you will see this very often. The broadcasting and reducing. The reducing, we already saw something like this before. And remember when we talk about MPI, OpenMP or OpenECC, the different threads were computing something, and at the end we were reducing. Actually, I put a better figure. I actually put a better, let me see. I can go into the figure of this, and that actually should be better here. So a reduce is like this. You have multiple instances, multiple processes that have some data, and we are doing some operation here to collect all that data. For example, a sum or a multiplication. And we will be talking here about this other option where you have some data and that you want to propagate across all the processes. So that's what we will be talking about. Okay, broadcasting. So here, this is example 03. This is example 03. This will never work. We have here one function, another function. Those are two different functions. I think I will be using this one only if I'm not. What I'm doing, I am basically, this is an example of a code that computes an integral using quadrature. So I am splitting some functions in a range. I'm getting a bunch of values in the domain, and I am spreading all those values on different machines for getting the sounds. And after I am making a reduce to gather all those values together. So What I'm doing here, I am sending the number of values. This one. This one was computed only by rank 0. So rank 0, okay, before this, everything was really normal. MPI need, com size, rank. This is really normal. Rank 0, what is doing rank 0? Rank 0 is computing how many slices this thing will be cut, will be distributing. So I'm making an agreement on a good number for distributing those across the number of processes that I receive during runtime, and this is the value that will actually be computed. So the first thing that I'm doing is only rank 0 knows this number, and I want all the processes to know this number, to get this value on their own versions of my end. So this, because it's broadcasting, is sending its value everywhere. All the processors are running this. Only rank number 0, source is master and master is 0, will be receiving from rank 0 this value. That's one thing. That's how you use the broadcast subroutine. So now what is happening here is rank number 0 associating different portions, so different limits for the integration. So one process will integrate, let's say, from 1 to 2. Another one will from 2 or plus something and to 3. And so they will split that. So what I'm doing here is that this is taking the decision. So rank 0 is in this schema, rank 0 is a master, is controlling the operation, is dividing the space, like again, like imagine a finite element code or something. Is deciding which are the different pieces that will be distributed across multiple processes. So this one is, with this computation, is getting the one extreme, the lower limit for the integral, and the upper limit for the integral, and is sending that data, this time using point-to-point communications, because every single process will receive different values for this. So they will sending those values. So here it sends A, and here it will send B. Other ranks will do the opposite. All the other ranks will first receive A here and will receive B here. Different values. Now that all of them have the same number of elements, but different A and B, they will be computing here what I'm doing here. Yeah, they are computing here the value of the function there, f1. So I'm using just one f1 function. And those are gathering those contributions to the integral in this my total. Here is computing all that. And at the end, I am calling for a reduce operation. So this is very similar what we did for OpenMP or OpenACC, and using the sum to gather all the partial values of my total and storing those in the total. So this is a reduction. At the end, rank number 0, master, will print that total, and that total will be the integral. Same thing you can do for multiple dimensions. It's just a different division. It will be a little bit more code, but the idea is the same. You have something that, imagine that this is particularly expensive, or happens for a bunch of points. You are computing something like a finite element and integration or something, or a molecular dynamics. This is something that takes some time to compute. So you are distributing that from different elements. You are later gathering all the data back into one single element. That's what is happening here. So this is one example. All this here for the two collectives that you just saw here, bcast and reduce. And this is one list of the several things that you can do with reduce. It's pretty much the same list that we knew from the other paradigms for parallelization. Reducing is something that we use a lot in parallel computing. So those are. Let me see if, okay, this is just a summary of the kind of elements that we saw here first. The main routines, I told you about those, send and receive, and we discussed about those. So now, in the next section here, I will advance. So we already saw this one, MPI bcast, MPI reduce, and now it's time for discussing a little bit more advanced routines like the scatter and scatter. So I did that with an example here. So this one is the let's say the sketch of how you use those two routines. They are very, very similar to the other collectives. Nothing in particular. Notice that when this routine, when you call those routines, all the elements in the MPI execution, all the processes should call those routines. So all this routine must be called by all of them. It's not just the element that is doing the scatter or the gather that calls the thing. It's all of them are involved in this. So here I have one example of an scatter. So what I did here, and I think it's right here, I put a different number here. I think it's number 11. Example 11. Yes, this is the example of a scatter. So what I'm doing here, the lines that we know, rank number 0 is doing this. They are allocating some buffers here, so some array. And I want a big matrix to be distributed. This is almost going into the direction of a domain decomposition, for example, for distributing the finite elements or CFD calculation, fluid dynamics. You are distributing an array to multiple domains. And this is the call that is doing that. So, and you will see how this works. So let's just compile this like that. MPI I4. I execute this. MPI run -p, let's say 8. This okay. Okay. So let's see if I okay. It will be a little bit more confusing. So I am making an array. Unfortunately, this terminal is making like is sending to a new line. I was not expecting that. So here I have an array, a big matrix here. This matrix has 8 columns here and 8 rows here, because I was running with 8 cores here. So what I'm doing here is I am distributing the array across different processes. So rank number 0 will receive one array from 1 to 8. Rank number 1 will receive the next chunk. Rank number 2 will receive another chunk. So each rank is receiving its own portion of the array. And that's how this scatter works. So I have a big matrix here, and I am distributing this matrix across multiple just one-dimensional arrays. There are these receive of, and here I am printing the receive of. So just to make, let me see, to make this a little bit clearer, I will make this slightly smaller. I will compile it. Yeah, now it works better. So I have this matrix, and each rank is getting just a portion of those elements. Now, similar to this, there is a gather, and I think I use it, I don't know if I use it for this example, we will see. But this is another example of a routine that uses collectives. Those are the main 4 collectives and variations of those. So for each one of them, there are several with non-blocking, blocking, buffering, non-buffering, the variations of those. Usually, this is all they use. And now, notice that when we were computing something here, we were all working pretty much together. So they were communicating to each other. So there is something more that we can do. That is something that eventually, for example, you do in the case of an molecular dynamics calculation or something, is dividing the space, dividing all those ranks, all those workers on different sections for different tasks. So in this case, we have, let's say, all those ranks that have been divided in 2 groups. And there is one communicator here for each of them. And they could do different things. So one of them could be focused on, for example, just in computing forces. Another will be just in charge of movement, or some dynamics, or changing some structure or something. So you can separate those workers on different sections. Imagine, for example, that one of those on a climate modeling thing, one dedicated just for land masses, another section dedicated just for air masses or continental modeling, and they are doing different things, and they are moving around, and they communicate later. They can communicate between them, but together they communicate just inside their own communication group. So that is the idea of communicators and groups. This is how some details about that, and I wrote an example here where I have a number of processes, and I am creating 2 groups. The first half of ranks will go for one group. So here, the first rank goes for one group, and I will create the groups here. And the second rank will go for the next group. So here I'm creating those groups. And each of them, this is just a small code. Each of them is just computing the sum, I think is, what they are doing a reduce or reduce. So they are gathering the value that they got from the others. So let's compile this. This one is, I think, example 12. And example 12. Yes. So here, I create two arrays here. They will contain the numbers of the ranks that I would like to group. So, so these ranks will go from 0 to, and let's say, imagine that I have eight processes here. So if I have 8 processes here, and I force this to be an even number, just to make things simple. So this array will have 4 values, from 0 to 3. And the other array here will have the other ranks, from 4 to 7. So here I am making a group of them, the first ranks, and here I'm making another group for the other ranks, and I dividing that depending on if they belong to the first group or the second group. Now, here I'm asking for a communicator for them, and here I'm calling an all reduce of the value that they are sending. The value they are sending is their own rank, just to make things easy. Their own rank. So they are sending the rank, they are receiving that value, and the value is reduced. The value is reduced here and reduced. So all of them, as I told you here, all of them are communicating to each other here inside their own group. They are just segmenting the operation. Now, how we compile this thing? Yeah, 12. And imagine that I'm doing this for 16, I think. 16 is okay. So the original rank was this, and by the way, there is nothing that prevents. So I will sort this just to get this. Sort minus k. Okay. So now I'm getting this one. So notice that those ranks here up to here got the same rank when they move into another group or to their own internal group, and they are gathering the sum of all those values, 0 plus 1 plus 2 plus 3. They are summing all these values here, 28. These other ranks here, from 8 to 15, are receiving new ranks inside their group, and they will compute with that all gathered the value of the sum, 92. By the way, I never mentioned this all reduce. This all reduce is similar to this one. It's similar to a reduce, but the value that has the answer are every single rank. Every single rank will have the value at the end. Different from the normal reduce, that just one rank will keep the final value. So that's the difference between the reduce and all reduce. And that's what I'm doing here. So at the end, all of them in the receiving buffer will have 92, the sum of all those values. Now, I think that's all that I have. There are more things here for communication, but I think this is enough for give you now at least a first exposition on this. And the exercises that I have proposed for you here are very simple. I hope that you can do it without much trouble, because basically it's picking and rewriting some of the examples, picking the right examples and making a small change for getting something like this. So writing a Fortran code that brings the rank and the total number of processes. So it's something, it's one of those that we already saw. This one is the integral for quadratures for the different function, the function that I never did. So it's just making a small change to the case that I proposed, from the case that I demonstrate for reducing. And this one is a little bit more challenging. This one is not something that is, but it will be, you can solve this if you pick the right pieces from the code. So this one, you have a long array, the random numbers, and you will spread that. So you will distribute that somehow. Each rank will compute the average of the data that they receive. And at the end, I want them to communicate the minimum and maximum of those values, to return from the collective operations, which was the maximum of those averages and which one will be the minimum of those averages. So it will be a couple of collectives. So it's relatively simple. We in the code, you can just even copy and paste and do minimal changes to get this done. That's all that I have. I hope that you enjoy a big overview on all those elements of Fortran and parallel computing. By the way, this material, it will be here. It's on GitHub. It will not disappear anytime soon. I will probably improve it for the next time. There are a lot of things that I would like to do. But you can review this later. So, yeah. So the material will be there. So don't worry. So thank you very much. I will be here. I will be here for the next hour. If you have questions, just send me a message here on the chat, and I will help you if you got stuck trying to do one of those exercises. Or sometimes at the very beginning, though, the errors are confusing. That's what is. This is not so simple. When something goes bad in an MPI code, sometimes it's not so easy to understand what was wrong, because it's usually one send that was missing, or you put a send or a receive inside a conditional, and not all the ranks are looking into that, right? So that's why having someone who has a little bit more expertise will pick the error quickly. So that's why I'm here. So if you want to do the exercise during the hour, I will be able to help you in case that you got stuck. So thank you very much. And thank you all of you who attend until the last day. I really, really appreciate that you show interest on learning this. There are not many Fortran programmers around. So I really, really feel motivated if you appear and you want to learn something from me during these days. Really, really appreciate it.